Oh, 4. Well, well, these 3 pieces, what I want to say is that the k-dimensional irreducible of SL2 has infinitesimal character k. I mean, our H star is naturally C, and that's the number, and so P n plus 1 of this M tensor M tensor F, it is the n plus 1 dimensional, and the P n minus 1 of M tensor F, it is this n minus 1 dimensional, the P n minus 3, it's the n minus 3 dimensional, and the others are 0. So I've explained that pretty badly. What coherent continuation is about is understanding this stuff. So let me try to make the definition. Here's the definition. A coherent family of always these things are virtual GK modules. It is a map. I think Greg often used capital theta, which goes from gamma plus x upper star to here. So this is what Peter talked about. This is the Grothendieck group of finite length GK modules. And so you can just think of this as formal Z linear combinations of irreducibles. So that's what this is supposed to be. And here are the properties that you want. The first one is that theta of gamma plus lambda, so this gamma is always fixed. And so this is in x upper star. I'll say has infinitesimal character gamma plus lambda. So means that all these irreducibles in this formal sum have this infinitesimal character. And the second property is that if you take theta, take one of these things and you tensor it with this is finite dimensional algebraic representation. What you get is the sum over the weights it's the multiplicity of that weight times the value of the character at the coherent family at gamma plus lambda plus mu. This is the so what this is saying this theta records all tensoring with F operations. If you take any one of these things and you tensor it with some finite dimensional, then this tells you what comes out. And it also, well, it also records these P gammas. Because of this first condition, well, I don't know. It tells you what the infinitesimal characters of all these terms are.
Sorry, with the prototype of this being finite dimensional.
Yes, absolutely. And I was about to. That's absolutely. I want to write that first for SL2. So here's, let me take gamma equals 0, and here's a coherent family of finite dimensional representations. Theta of n, so this is any integer. I mean, it's an element of gamma plus x up per star, so it's 0 plus an integer. It is equal to the n-dimensional irreducible of f. This is if n is bigger than 0. It's minus the n-dimensional irreducible of f if n is less than 0, and it's 0 if n is equal to 0. So this is the n-dimensional irreducible of SL2. I should have said SL2, sorry. So for a negative dimension, you have to understand that it's just it's only in the Grothendieck group, and it's minus. And now what the claim is that if you take the n-dimensional representation of SL2 and tensor it with any finite dimensional, what you get is the sum over m, a weight of f, of the n plus m dimensional.
And how it's precise? It's not just.
Well, this is a statement in the Grothendieck group, because let's look at it. Let's take the two-dimensional and tensor it with the four-dimensional. This has weights 3, 1, minus 1, and minus 3. And the formula says that what we get is the five-dimensional, the three-dimensional, the one-dimensional and the minus one-dimensional. And these two terms cancel in the Grothendieck group. What this minus one-dimensional means the negative of the one-dimensional, and so they go away, and you're just left with 5 plus 3, which is the right answer for tensoring in SO2. So this, this is a standard formula. I mean, works for any tensoring with, you can, well, in Humphreys, I mean, it's not, you can find a formula for decomposing a tensor product using the weights of the second factor, something like whichever. I mean, basically this kind of formula, and it's well, I should say that if we take any G and no, let me not. Anyway, that's a coherent family. Yes.
So for SL2R, all the finite dimensionals lie in the same coherent family?
Yes.
And is that a true statement for arbitrary tree?
So let's do that over here. So let's see if I can make this statement correctly. So for now, if I take any G, I want to take gamma equals rho and make a coherent family on X upper star plus rho, and the value at, well, rho plus lambda, where this is this is in X upper star, excuse me, is going to be minus 1 to the length of W times the irreducible of highest weight W of lambda plus rho minus rho. This is what happens when lambda plus rho is regular and W of lambda plus rho is dominant. So if lambda plus rho is regular, there's a unique Weil group element that makes it dominant, and so I can do that. And I just put 0 if lambda plus rho is singular. And so in particular, if lambda is dominant, if lambda is a dominant weight, this theta of lambda plus rho is the irreducible of highest weight lambda. So that's what you were asking, Jonathan. This is a coherent family that has all of these finite dimensional algebraic representations in it. And the way you extend it, well, so actually you can see this very nicely. The picture, here's H star. Well, this is the familiar case when the Weil group has order 10. So this is the dominant chamber. And here you have irreducible finite dimensional representations. And in here, you have minus the irreducible finite dimensional representations. And in here, you have the irreducibles again, and then minus. Anyway, that's the story. In every chamber, you have the same representations, but appearing with signs. And what this might suggest to you is that these finite dimensional representations have something to do with the sign character of W. Okay. So, what shall I think I'm going to leave the definition up there. And so here's the basic theorem. So suppose gamma in H star is dominant, doesn't matter, and M is an irreducible GK module of infinitesimal character gamma. Then the conclusion is that there's a unique coherent family of GK, virtual GK modules. Maybe I'll call it theta sub m of gamma plus lambda for lambda and x upper star, characterized by the first property is the most obvious one. The value at gamma is equal to m, so that's good. The second is that if gamma plus lambda is dominant, then this theta m of gamma plus lambda is irreducible or zero. And that's the whole characterization. And I think I'm okay here. So, how do we get Weil group representation?
Do you really need two?
To characterize it uniquely, yes. So,
Yeah.
if gamma is regular, 2 is a consequence of 1. But if it isn't, it isn't.
So what is the advantage of putting n in perfect precision?
Now we can make a Weil group representation. If I just hand you a finite dimensional representation of G, where's the Weil group representation? But if I hand you this picture, the sign character of the Weil group is staring at you. And What?
So in this theorem, if I take n to be the trivial representation, I'll get all the finite dimensions.
You'll get this family that's written over here. That's exactly right. This, yeah, I mean, this is the theta for the trivial on rho plus x upper star is the one that's written over here. Okay, so what I want to say, let's do it over here. So a coherent family it's a map which goes from it goes from x upper star plus gamma to virtual GK modules. If we fix gamma, this set of all coherent families well, on x star plus gamma, it is a finite rank Z module, free Z module, with basis given by these theta m's for m is an irreducible GK module at some fixed regular gamma plus lambda. So yeah, if I take, well, I said that you got these families attached to irreducibles, and well, the theorem tells you this. So this rank is the cardinality of all param whatever it is that, well, and you have to put G in here somewhere, I forget, but
Lambda is also fixed.
yeah, I mean, so the punchline was supposed to be Weil group represented. Yes. I fixed gamma, but you know, if I'm talking, for example, about a compact group, and I fixed gamma equals 0, there's nothing, there's no representations there. So I wouldn't see anything if I only talked about modules at 0. I need to move to some regular place in order to be sure of seeing everything.
So the coherent family is it characterized by gamma?
A coherent family is a map from a certain coset of the weight lattice to
Is gamma allowed to error?
no, gamma is fixed. There's one gamma for each family. So here I'm looking at the set of all coherent families defined on one particular translate of the weight lattice. So where's the Weil group representation? So the integral Weil group I guess W sub lambda, it's the set of gamma, W sub gamma. It's the set of W in W such that W gamma minus gamma is in, well, it's in the root lattice. This is equal to W gamma plus lambda for lambda and x upper star. What I want to say is So the sort of obvious fact is that if I have some W in W gamma and this theta is a coherent family on gamma plus x upper star, then I get a new coherent family. W applied to theta, whose value at gamma plus lambda is, by definition, the old coherent family at W inverse of gamma plus lambda. And the thing to notice, I mean, this is gamma plus lambda plus the sum of roots. And so this is defined. I mean, it's gamma plus something. I mean, this thing is in x upper star. So this is defined. And this thing, this has infinitesimal character W inverse of gamma plus lambda, which is the same thing as the infinitesimal character gamma plus lambda. So it satisfies condition 1. I've killed it again. So this says that it's that this W applied to theta satisfies condition 1 in the definition of coherent. And condition 2 is true since the weights of F are W invariant. The weights in their multiplicities are W invariant. So that condition comes along for the ride too. And so the point is that this gamma gives us a representation of this W gamma on these coherent families.
Well, this has a Z basis given by the irreducibles at some regular gamma plus lambda. So you get a W gamma action on irreducible modules. And well, so each irreducible module generates a representation of this integral Weyl group. And that's what the coherent continuation is. The definition is completely different from the Hecke algebra stuff for GLN over a finite field. Nevertheless, the nature of this invariant has a lot in common. Well, I don't want to. What do I want to say? I shouldn't say. Maybe I'll just say 2 words about a common property. In this, so now we have an irreducible GK module, we get this coherent family which generates a W gamma representation, which this appears in some symmetric power of H for well, it hits the symmetric power of H for minimal D, and then what, I forget, Peter talked about this, the GK dimension of the representation is D. So what's the finite field version of that? So the finite field version said that an irreducible GLN FQ representation with a B fixed vector I said corresponds to an irreducible representation tau of the symmetric group, which appears in SD of H for some minimal D,